All right, we've got a lot of ground to cover to consider protein structure. So we're going to start all the way at the base at the bottom, and we're going to talk about what makes up proteins, the connection of amino acids together. And so I'm going to talk about two chemistries here on this slide. On the left half of the slide, we're going to talk about the chemistry that happens between the two main functional groups we see on amino acids, a carboxylic acid and an amine, and condensation of those two functional groups to create a linkage creates an amide linkage or a peptide bond. So we'll go through all those details in just a minute. On the right half of the slide, I'm going to talk about one of the chemistries that can happen between specific side chains, specifically cysteine residues that have a thiol functional group. That thiol functional group is going to connect with another thiol functional group to create a disulfide linkage. And so we're going to understand how that chemistry happens. So to start here, let me just split my page down the middle. And I'm actually going to zoom in on the left. I've got a lot that I'm going to write here. This is going to be kind of a dense slide, but we want to make sure that we get sort of all this information in here. Okay, so first, let's just take a step back and make sure that we understand the basic structure of every amino acid. So every amino acid has an amino group, has a carboxylic acid group, and has an alpha carbon in the middle. So we're always going to be looking for this N-C-alpha carbonyl sort of pattern. And that's going to be important when we look at protein structure, not just amino acids. So every amino acid is going to have this N to C sort of directionality, and we're going to see that directionality again when we talk about making peptides and then large proteins. So let's review again some of the basic parts that we have here with an amino acid. So again, we're going to have an amino group and we're going to have an acid group. Remembering our pKa values, amino groups, protonated amine groups, have pKa's around 9 to 10. So at physiological pH, which is less than that, that means that our molecule is going to stay protonated. So we're always going to see amines physiologically going to be in a protonated state. Now, I say always, we might see a unique situation where we have some pKa shifting, but for the most part, amines are going to be protonated under physiological pH. Contrast that to the carboxylic acid. Now, carboxylic acids are going to have pKa's in the 3 to 5 range. So again, that's going to mean we're in a situation where we're going to be deprotonated at physiological pH. So this creates a unique situation where we have a plus charge on one part of the molecule and a minus charge on the other part of the molecule. But it would be incorrect to say that this molecule is uncharged. What we can say is that this molecule has no net charge. And that's not, again, saying that it's uncharged, but molecules that have charged species that end up balancing one another out, so we have no net charge, are given a special name. We call these Zwitter ions. And so amino acids are a great example of a Zwitter ion. Okay. One more thing to highlight with amino acids, when we've got this C-alpha carbon, we can see that there's 4 things attached to it. And when we have 4 different things that are attached to a carbon center, that can create a chiral center. So every amino acid has an amine group, has a carboxylic acid group, has a hydrogen, and then has an R group. So with the exception of glycine, where that R group is a hydrogen, every amino acid has a chiral center at this alpha carbon. So this chiral center always has the same stereochemistry, and it is going to be of the L configuration. So if you need a refresher and a reviewer on the differences between all of these kinds of ways that we represent stereochemistry, remember on Blackboard there's that sheet that highlights there are experimentally derived kind of notations for stereochemistry. That includes plus and minus, and then lowercase d and L. Those are experimentally determined. There's experimentally related stereochemistries like uppercase D and L, which we're going to see with amino acids here and then for sugars. That's experimentally related. And then you probably have the only form of stereochemistry maybe you learned in an organic chemistry class, which is R and S. And that's really just an on-paper kind of determination of stereochemistry based on prioritization of groups around a chiral carbon. Okay, so let's move on now and talk about the chemistry that we're going to have here. And so I want to highlight that the chemistry that's happening is between a carboxylic acid functional group and then an amine functional group. And what we have here is what's called condensation chemistry. You can think of it meaning, yeah, we're condensing things together, but it's called condensation because a small molecule like water is eliminated. Later on in the semester, we're going to learn about the reverse process, which is the use of water to break this bond, and it's going to be called hydrolysis chemistry. But in this forward direction, condensation chemistry combines a carboxylic acid with an amine, and it generates this peptide bond. So we've got our peptide bond here, right, which is an amide linkage. So let's talk a little bit about how this happens. Remember, our first three reaction mechanisms tried to form this amide bond. The first one, where we just took a carboxylic acid and an amine and put them together, that doesn't make an amide linkage because it just does acid-base chemistry. Then we had an amine with an acid anhydride, and we could form an amide linkage there, but that's not the chemistry that we tend to see under biochemical conditions. So finally, with reaction mechanism 3, we had a good leaving group and an OAMP group, and we were able to do that condensation chemistry. So what we're going to see here is a reminder about when we do these kinds of chemistries, somebody has to be a nucleophile and somebody needs to be an electrophile. Well, I hope one of the patterns that you've recognized is carbonyl-containing compounds are often our electrophiles, and then heteroatoms, such as nitrogen or oxygen, that have lone pairs of electrons are likely to be our nucleophiles. Well, here's the problem with what's going on in this situation. This carbonyl-containing functional group as a deprotonated carboxylic acid is actually a poor electrophile because in a deprotonated form, it's fairly electron-rich. Contrast that to a protonated amine. We want it to be a nucleophile, but it's actually a poor nucleophile because there's no lone pair of electrons. And so that's problematic for that functional group. So we're not going to worry right now about how this chemistry happens, but we have to have some differing things that happen in order to condense these two functional groups together. All right, so moving on now, and again, thinking about the chemistry for what we see here once we do form this peptide bond. In this case, one amino acid plus another is going to generate this little dipeptide. So let's go through a little bit of the anatomy that we see here with this peptide. Like we saw with amino acids, we're going to see a directionality, and we want to be looking for that N-C-alpha carbonyl. N-C-alpha carbonyl. And we're going to use that directionality to make sure that we can see the N to C direction in a peptide or a full protein. Just to highlight, it's a little bit of semantics with words here when we talk about peptide versus protein. Usually peptide represents a short portion of a protein, so maybe a section of it, and protein typically refers to something larger or the entirety of a molecule. So this end, not surprisingly, is called the amino terminus, or sometimes called the N-terminus. And then this end is called the carboxy, or the C-terminus. Okay, so what we've made here by condensing two amino acids is a dipeptide. If we had three amino acids that we connected together, it would be a tripeptide. Okay, and we'll notice here are the two side chains that we'd have. So the last thing that I want to just do is teach you how to draw a peptide, because one of the things you're going to have to do on an exam is I'm going to give you a little peptide that you have to draw, and it's usually some cute word that I'll put together, maybe like smarty or thrifty or something like that, that basically uses the 20 letters from the alphabet that I can make a word from and asks you to make that into a little peptide and then attach the amino acids on there. So we're going to go through how to do that, and I'll give you a couple tips for sort of the levels that you can have in terms of points that you can earn. Okay, so when we think about this direction, again, it's N-C-alpha carbonyl. So I want you to remember that pattern because that's going to be helpful as we draw our structure here. So we always start with our N-terminus. So here's our N. So watch me do this, and then I'll go back and I'll retrace it with my highlighter. So it's N-C-alpha carbonyl. N-C-alpha carbonyl, N-C-alpha carbonyl, N-C-alpha carbonyl. So in doing this, I've generated, here's 1, 2, 3, 4 C-alpha carbons, which means I've generated a 4 amino acid peptide. Okay, so kind of putting the rest of our pieces in here, every nitrogen is going to have a hydrogen and a lone pair. Okay, so we've got our 4 peptide bonds that we have there. On all of our alpha carbons, we're going to have our R groups. Okay, so here's how you could have different levels of points that you could earn when you do this, for example, on a test. So if all you did was write the amino acid single letter code there. So let's say that we had RAIN, R-A-I-N, okay? Just putting that letter there would give you sort of the base level of points because you're like, I know there's a side chain that goes there, but I don't know anything more about that. So again, if we had R-A-I-N, R is going to be arginine, A is going to be alanine, I is going to be isoleucine, and then N is going to be asparagine. So if all you did was put the letters in, you get your base level of points, okay? One more level up is saying, you know what, I don't remember exactly what that structure is, but I sort of remember what the functional group is. So if you were to put in the functional group, for example, saying that arginine, right, is going to have that arginine kind of, nitrogen basic containing functional group. Alanine was going to have a methyl group. Isoleucine was going to have, and you could just say it was nonpolar because if you don't remember the structure, you just remember that it's nonpolar. And then asparagine is going to have that amide group at the end. So you could put those pieces together, and that's the point I want you to get to, where you just know those pieces of information. But full credit is going to be, hey, I'm going to put in these amino acid side chains. I'm going to draw them in like they look. So different ways that you can then represent kind of the structure of a peptide. But at its core, start with the peptide backbone, recognize where you put your side chains, okay? And then for different levels of credit, indicate how well you know what those side chains are. All right, so that's what we have sort of on the left as we think about chemistry that happens between the amino and the acid functional groups that every amino acid has, okay? On the right here, now we're going to go into some details to think about chemistry that happens with one specific side chain, and that's going to be our cysteine residue. So cysteine residues have a thiol functional group here. So that's the thiol functional group that we have. And the thiol is really the reduced form of this functional group. So one of the things that's really important to be able to think about is to look at functional groups or the differences between molecules and tell who's the oxidized state and who's the reduced state. So as a general rule of thumb, we might be looking at the amount of hydrogen that we have there. The more hydrogen that we have, the more reduced that functional group is. So once we get to a disulfide linkage, so that's what we have down here. This is a disulfide linkage. And this is the oxidized form. And we can see that's a sulfur that doesn't have any hydrogen on it. So it's much more of an oxidized species. Okay, so what happens here is we have redox chemistry. So if these two thiols come together, form a disulfide linkage, and they are oxidized, it must mean something else is reduced. And what we show here is that molecular oxygen can be reduced to water. Okay, so that is the reduction part of the reaction that occurs. But we can also show this very generically by showing that there's some kind of an oxidizing species that then becomes reduced. Okay, so this is our reduction sort of chemistry. So O2 is the oxidized form, H2O is the reduced form. So why is this important? Okay, this is the story of glutathione. And we're going to see glutathione at several points sort of throughout the semester. Glutathione is kind of your natural antioxidant in your body. Okay, so we're going to abbreviate glutathione as GSH. So G reminding us that it's glutathione. We'll actually look at the structure of it in a little bit here. But G for glutathione, and then reminding us that it has a thiol functional group. So here's how this works. You're going to have 2 glutathione molecules, okay? And then it can undergo oxidation to generate a disulfide. So again, this is the reduced form as a thiol. This is the oxidized form as a disulfide. Okay, so that's an oxidation process, and highlighting that oxidation doesn't happen without something else being reduced. So in this case, we can have O2 undergoing reduction to generate H2O. So this is a paired process. Let me give myself a little bit more room here. This is a paired process. So it's a paired process, which is a redox process. Okay, and so at the end of the day, it can be molecular oxygen, but it can really be any oxidizing species that ultimately is neutralized. So the last little piece, just to kind of highlight here, and I've mentioned this already, but just to kind of put it down in words here, when we talk about something that is oxidized, okay, oxidation we can think of as the loss of electrons, but I also want you to remember to be able to look at molecules and see that if you've increased the number of oxygen atoms and or decreased the number of hydrogen atoms, that's a good indication that that process, the functional group change, is an oxidation process. On the flip side, reduction is the gain of electrons, and we can also think of it as decreasing the amount of oxygen in a molecule or increasing the amount of hydrogen. So one of the important skills that I want you to be able to do is, if you look at 2 functional groups that undergo changes, be able to see, is that an oxidation of that functional group or is it a reduction of that functional group? Because that's going to often be a clue with other kinds of chemistries that might be going on. All right, so lots on this slide. It was a lot to sort of build together, but really kind of gets us thinking about how we couple amino acids together to begin to string those monomers together to make the polymer that are peptides and proteins, and then also to begin thinking about, well, chemistry can also happen with the functional groups that we have on the side chains in those amino acids. Okay, so we're going to continue to build on this as we start to think more about protein structure.